Hi everyone. Today we will continue with the section about step functions, and also we will do solutions of ODEs where the forcing function is discontinuous. So let me just remind you what we did last time. So we talked about this unit step function, and this function was 0 when t is less than c, and when t is bigger or equal to c, it was 1. And we computed its Laplace transform. And what was the Laplace transform of this? UCT. This was equal to e to the minus cs times 1 over s. Furthermore, by using this thing, we were able to write discontinuous functions in terms of unit step functions, and we were able to compute their Laplace transform. But for this, we did the following formulation. Remember, so this is the first thing maybe we did. Second thing now, and when you take the f of t minus c, and if you multiply this thing with uct, then this was equal to e to the minus cs times f of s, where f of s is equal to the Laplace transform of f of t. So remember the formulation I was using, like rather than saying it's a function, I was saying it's a signal, and then you have let's say a signal like f, and which starts from 0 to infinity, and let's say its Laplace transform is capital F. Then what does this formulation says? So f of t minus c says there is a basically you are shifting to the right your signal, and then when you multiply with this unit step function, it says that between 0 and c it's completely 0, and then after c then it becomes just the f shifted. So if, in terms of signal formulation, this means there is a delay in your signal. So if your signal starts late, and then what happens in the Laplace transform, it says that just take the Laplace of the original one, not shifted one, and multiply this thing with e to the minus cs. That's the reason, like for this one, you can formulate it as like 1 times uct, and uct will give you e to the minus cs. The Laplace of 1 is going to be 1 over s. And so as a result of this, we can just do the inverse Laplace transform. Inverse Laplace transform is if you have e to the minus cs times f of s, just this is going to be uct times f t minus c. This is what we are going to have. All right, we did some examples, but let's do some more. Now let's our first three examples were computing the Laplace transform. Now let's talk about the inverse Laplace, and then we can do some mixed examples. So let's first of all try to compute the inverse Laplace of e to the minus 2s times 3 over s squared plus 1. So let's try to compute this thing. Now, this formulation says that when you see e to the minus 2s or e to the minus, when you see e to the minus cs, you will understand when you just take its inverse Laplace, there must be a unit step function. So that's the reason we will just worry about this portion, okay? This will eventually give us just a step function. So then what will happen here? This will give me u to t. Then, because we have e to the minus 2s, according to the formulation, this is what we have. Now, I need to look at the rest, which is 3 over s squared plus 1. And we know inverse Laplace is linear, so we don't need to worry about 3 here. So I can take 3 out. So it's all about 1 over s squared plus 1. So 1 over s squared plus 1. And if you remember this is the Laplace of sine function, sine t. So it says that now I basically write it's the Laplace transform of sine t. But according to formulation, you will not write sine t, you will just shift it with the amount of the c there, which is 2 here. So I will not write t, but I will write t minus 2 there. So because 2 is our c, and t, I will not write t because sine t's Laplace is 1 over s squared plus 1, but in the formulation I need to write the shifted version because of the u2t, there is a delay in the signal. All right, now number 2. One minus e to the minus 21s over s squared. Again, this is something similar to the previous one. So in this case, again, I will use the linearity of the L inverse. So this is going to be L inverse 1 over s squared minus L inverse e to the minus 21s over s squared. So I already know this. This is just t. And minus, now I see that there is e to the minus 21s. So this will remind me that there should be a step function at 21. And now I just look at what is left. The left part is 1 over s squared. And we know that its inverse Laplace is again t. But I cannot write here t. I have to write its shifted version by using 21. So I will write there t minus 21. Right? All right, our third example is L inverse of e to the minus pi s over s squared minus 2s plus 2. Let's try to compute its inverse Laplace. So this time again, I mean, when we see exponential in the s domain, we just understand in the t domain it will give us just a step function. So then it's all about then just what is going to happen here. It's all about this. And this part must be written in terms of well-known pieces. So if you look at now s over s squared minus 2s plus 2, by using the partial fraction idea, either I write it the bottom if it is factorizable by using linear factors. If it is not factorizable, I have to write it as a complete square. And as you can easily see, this is not factorizable. There are not real roots. So if you write it, we will get s minus 1 square plus 1 square. Okay, this is what we have. S over s minus 1 square plus 1 square. So I see that there's a shifting in the s domain, but that shifting is not seen in the s above. There is just s minus 1, but some part is shifted, some part is not, so I have to arrange it. So whenever I see an s minus 1, all the terms must be written in terms of s minus 1. So I understand everything is shifted in the s domain. So that's why I will just play with this. So if you, rather than writing s, I'm going to write s minus 1, but I cannot change the problem, so I have to add 1 here, so I get the same thing. S minus 1 square plus 1 square. So now you see everything is written in terms of S minus 1. So you can now separate this thing. S minus 1 over S minus 1 square plus 1 square plus 1 over S minus 1 square plus 1 square. So in both things, there is a shifting in the S domain. So if there's a shifting in the S domain, how do you get shifting in the S domain? Then in the t domain, in the time domain, you have to multiply with an exponential. So what exponential? E to the AT shifts S to S minus A. So here we see S minus 1. So that means I have to multiply e to the t with e to the t in the time domain. So now let's go back to our original question. E to the minus pi s. So I understand this is u pi t. Now it's written as separate pieces. These are shifted in the S domain. So in the time domain, there must be an exponential. So there must be an e to the t here. And this is exactly, I mean, if you just erase all the shifting, this is just a cosine function. So we see this is cosine t. But now, if there weren't any unit step function, I would write this. So if there weren't anything like this, I would write this. But if there is a step function here, then I have to shift all of them with the pi amount. So I have to write here t minus pi and t minus pi in the place of t. And similarly, when you come to this, this is a shifted, now it's again with one amount, but it's exactly this sign. So again, we will do now t minus pi, but this time it is sine t minus pi. So this is what we get for the Laplace of this, inverse Laplace of this function. All right. Now, let's do something reverse. Again, since we already know now the Laplace transform of the unit step function and unit step function times a function, so we can compute the Laplace transform of a discontinuous function now. So f of t, we are given the following signal, which is 0 when it is less than 1. When it is between 1 and 2, it's constant, which is 3. And when it is between 2 and 3, it is 4. And when it is bigger than 3, it is t squared minus 8. Okay, this is the thing. You can, if you want, you can graph this signal, but I will not do it. So now you know how to write this. Let's do it in two ways. So first way, we just look at the heads of the our signal. So head means like non-zero terms. So we have non-zero term here between 1 and 2, non-zero term between 2 and 3, and non-zero term after 3. And as you remember, this was arranged by using the step functions. So if you look at f of t, so my first non-zero term is happening between 1 and 2. So we know that if you write u2 minus u3, so this one now, if I just write this, I know that this is 1 between 2 and 3, and otherwise it's completely 0. So if I multiply this thing with 3, this means that if I just write this, this is 3 between 2 and 3, so between 1 and 2. Oh, my bad. So this is going to be 1, and this is going to be 2. I'm sorry. That's okay. Between 1 and 2, it's going to be 3, and the rest will be 0. So, but then there's another head, there's another non-zero part of the signal between 2 and 3. So if I write u2 minus u3, this thing says that it will be 1 between 2 and 3. If I multiply with 4, it will be 4 between 2 and 3. The rest is 0. So that's the reason this is only affecting between 1 and 2. This is only affecting between 2 and 3, otherwise 0. And now after 3, so now I write here u3t. So before it is 0, after it is what we have here. And so t square minus 8. So this is the, but now after this you have to do algebra of this one. So if you look at, we have 3 times u1t minus, so if you look at here we have minus 3u2, 4u2, and so when you add them up you get plus u2, and then now this part is over. We have now minus 4u3, but we have also t square minus 8u3. So in the u3 parentheses, we will have t square minus 8 minus 4. So we will have t square minus 12. So this is what we have here. Okay. And the second method was the following. I will get the same thing, but directly, not without doing any algebra of these step functions. Second way. Now, you can check from the notes. So I start writing. So how is my signal starting? My signal is starting at 0. So I don't need to write because 0 is just the identity element of the addition. So, or if you want, you can write. It will not matter. So your signal starts at 0. If you don't touch, it will continue at 0. But then something is happening. Starting from 1, it changes. So that means there is a change coming at 1. What is that change? It was previous to 0, now it becomes 3. So then I write it 3. So this way now, my signal became 3. And now it continues as 3 forever if I don't touch. But now it doesn't continue that way. And when you come to 2, things change. So it means something is changing at 2. So I should arrange it. So I write u2t, which says I will affect after 2 before I don't do anything. So previously it was 3. Now it was become 4 because between 2 and 3 it's 4. And so previously 3, to make it 4, I should add 1 to this. So 1 plus 3 becomes 4. And this is affecting after 1, this is affecting after 2. So together they are affecting after 2. 3 plus 1 is 4. But then if I leave like this, it will continue forever. But there's another change coming. That is at 3. So that means I should write here 3. So which will affect starting from 3. What is that change? So previously, now my signal was coming as 4. I will have to make it t square minus 8. So I should add t squared to this. And now 4, and to make it minus 8, I have to subtract 12 from this. So if I leave like this, then I should add this thing with this one, so you eventually get t squared minus 8. Now, let's compute the Laplace transform of this after writing. So we have u1 t times 3. So this is exactly e to the s minus s times 3 over s. So u2t's Laplace e to the minus 2s times 1 over s. And when you come to this, now it will be e to the minus 3s. But now, these were constant and there were problems. But when you come to this, to use the formula, this part must be written not in terms of t's, but in terms of t minus 3's. So that's the reason we should do some extra work, and we have to write this part in terms of that. So let me just open a parenthesis here, and I need to express t squared minus 12, not in terms of t's, but in terms of t minus 3's. So rather than using t, I can use t minus 3. So I'm writing t minus 3 squared. Are they equal to each other? Let's check. This is t squared, okay, but we have minus 6t coming. But there is no minus 6t here. The equality is not satisfied. So I should add 6t to this. But I cannot use t's anymore because I have to use t minus 3's to write it in terms of t minus 3. So rather than using t minus t, I'm using t minus 3. Okay, so I'm trying to replace all the t's to t minus 3's, but the equality must be preserved. So we have now t squared on this side. We have minus 6t coming, now plus 6t, so they are canceling, no 6t here. Then, so we have plus 9 here, okay, but we have here minus 18, so we have minus 9, so then I must have minus 12, so I should subtract 3 from this. Now if you look at, if you expand it, you exactly get the same thing, t squared, minus 6t plus 6t, they cancel each other, so we have plus 9, so minus 18, we have minus 9, minus 3, so minus 12. So I was able to express t squared minus 12 in terms of t minus 3's. But remember, when you are going to write its inverse, you should not think the shifted version, but just the original version. So what is the original version to get this expression? Of course, you must have t squared plus 6t minus 3. And then in the t, if you replace all the t's with t minus 3's, you get this expression. And so then I need to take the Laplace of t squared, which is 2 over s cubed plus 6 times Laplace of t, which is 1 over s squared, minus 3 times Laplace of 1, which is 1 over s. Now, be careful. To use the formula, I have to express this in terms of not t's, but in terms of t minus 3's. This is the expression. But then when you are going to write the Laplace, you will not write the Laplace of this, but the original Laplace, which is non-shifted version, which is t squared plus 6t minus 3, as you can see here. All right, so now we learned this, so we can use them now to solve differential equations. So this is basically section 6.4. Okay. .4, solving differential equation with this continuous forcing function. So we can write the name. So I will just do an example. So let's solve the following initial value problem. Y double prime plus y equal to t over 2 when it is between 0 and 6, and when it is after 6, it is 3. And our initial conditions are y0 is equal to 0, y prime 0 is equal to 1. Okay? Now, you can understand the problem in the following way. Like if you look at the coefficients here are both positive. So I can think this like as a mechanical vibration spring mass system. So I have a spring and a mass attached to this. So here we have M, m is equal to 1, which is the coefficient of y double prime, and k is equal to 1 again, which is the spring constant. And if you look at gamma is 0. So it's an undamped spring mass system with m1 and k equal to 1 unit. Okay, so then what does it say? So you have such a spring mass system. Initially, it was at rest. Y0 equal to, sorry, not at rest. Initially, it's at the equilibrium position. Y0 is equal to 0. But it has a certain velocity initially, which is 1 unit. It's plus, so it's 1 down. So at the instant 0, at time 0, it was at equilibrium, but with a velocity downward with 1 unit per second. Okay, and then you start applying external force to this. What is an external force? When the time is between 0 and 6, you apply an increasing force, which is T over 2. So at the beginning it's 0, then it's an increasing force. But starting from 6, your force becomes constant, which is 3. So you apply, you can say 3 unit force. So if you look at actually your force, if you look at, let's say this is your force, and if you try to graph it, so this is 6, this is 0, this is 3, so it's coming as linearly, so it's linear, constant, so slope. So then after that it continues as 3. Okay, so you apply an increasing force starting from 0, and then you apply a constant force. So this is what we have. It's not discontinuous actually, it's a continuous thing, but it's piecewise defined function. It's not the same function everywhere. So now what we are going to do, we will try to solve this problem. And if you are interested, you can solve this problem by using the previous method, by using the method of undetermined coefficient. But you will see, I mean, it will give you a headache. You have to do lots of computations. Now let's use Laplace transform to this. Now to use the Laplace transform, first of all, I have to take the Laplace of both sides. But to take the Laplace of both sides, I need to take the Laplace of the forcing function. So that's the reason. Let's write the forcing function in terms of unit step functions. So now, what is the thing? So initially it was coming as T over 2. So, but then a change happens when the time is 6. What is that change? It becomes constant as 3. So it comes, so to arrange that, so at 6 now I have to change it to make it 3. So it was T over 2. So I should kill first of all this T over 2 by adding minus T over 2. Now it became 0, but I have to make it 3. So I should add 3. So then if you leave like this, before 6 it is T over 2. But after 6, it's the sum of these two, which is just 3. So if you reorganize it, then if you take a minus out, use 6t. What do we have here? So this is exactly t minus 3. So then if you just make the denominator same, so we have t minus 6 over 2, so I can put over 2 out. So we are lucky, it's already the shifted version. Now, so let's take the Laplace transform. Y double prime plus y. And Laplace of f of t. So from this, we get s squared y of s minus s times y0 minus y prime 0 plus Laplace of y is y of s. The other side is the Laplace of this. T over 2's Laplace is 1 over 2 times 1 over s squared and minus 1 over 2 times u6t. So we will have e to the minus 6s. T minus 6 is already shifted, but the original version was t, so it's the shifted version t minus 6. So we have 1 over s squared. This is what we have. What are the initial conditions? y0 is 0. Y prime 0 is 1. So from this, we get the following. So if you take y of s parentheses, we have s squared plus 1. If you take everything to the other side, there's only one non-zero term here, which is minus 1. If you put other side, it becomes 1 there. And we have 1 over 2 times 1 over s squared minus 1 over 2 times e to the minus 6s times 1 over s squared. So then if you divide everything by s squared plus 1, so we have 1 over s squared plus 1 plus 1 over 2 times 1 over s squared times s squared plus 1 minus 1 over 2 times e to the minus 6s 1 over s squared plus 1. So basically we found the solution's Laplace. So then what is the solution? If you can compute the inverse Laplace of this, then we will be able to find the solution. So what is y of t? The solution we are looking for to this initial value problem. It's all about computing the inverse Laplace of this. Actually, we know this part. We know this part. It's just exactly sine t. But when you come to this part, we have to do, again, now partial fraction method for this part. And when you come to this one, it's actually, we have an e to the minus 6s, but we know that this doesn't cause any problem. When you take inverse of this, this will bring us a unit step function. So it's all about what's happening next to this. But it's the same thing as the previous one. So that means if I can find the inverse Laplace of this, then it's the same thing repeating here. So I can compute everything here. So that means it's all about then 1 over s squared times s squared plus 1. So we have to use partial fraction to compute this. So then, how are we writing? So we have 1 over s squared plus 1. This is s squared, which is s squared, which is a linear thing. So we write a over s plus b over s squared plus, now we have s squared plus 1. This is quadratic term. For the top, we will write cs plus d. Then we will compute this a, b, c, d. So how do we do this? We multiply this thing with s times s squared plus 1. We multiply this thing with s squared plus 1. And we multiply this thing with s squared. If you do this thing, then we get, now we have s cubed times a. So also we are getting cs times s squared, which is giving us cube. So we will have s cubed term whose coefficient is s cubed times a. We have an a here, and we have a c. So we have a plus c. Now how about s square terms coefficient? And we have a times s here, nothing coming. B times s squared, so we have a b. And we have d times s squared, so we have plus d. Now s term, and we have a s and nothing coming, so we have a s. And then the constant term plus no constant coming here. We have b here and no constant coming there, so just we have b over s square plus 1. Okay, so if you equate to the other side, we see that a must be 0 because there is no s term. There is no s term here. So a is 0. And b is the constant term, so it must be 1 because that's 1 here. And now a plus c must be 0 because there is no s cubed. A is already 0, so and c must be 0. B plus d must be 0 because there is no s squared terms. B is 1, so d must be then minus 1. So now if you look at, then we have 1 over s squared plus 1 can be written. No a, we have b, we have 1 over s squared, and no c but just d minus 1 over s squared plus 1. So according to this now, 1 over s squared, 1 over s squared plus 1. So if you look at this part, we have 1 over 2, and it's 1 over s squared minus 1 over s squared plus 1. 1 over s squared's inverse Laplace is t. The other is sine t minus 1 over 2. This will give us u6t. And again, it will give us t minus sine t if you take inverse Laplace. But because of the step function, I have to shift them with the amount of 6. So we have t minus 6 minus sine t minus 6. So this is what we have. Okay, so we don't do any arrangements, as you will see probably in one of the conceptual problems later. So we just attack the problem by using Laplace transform, and eventually we get the result. So in this section 6.4, I just want to do only one example because it's just solving differential equations, and we know how to solve differential equations by the method of Laplace transform. And it's all about computing the Laplace of the forcing function, which is written in terms of the unit step functions, plus then you just take the inverse Laplace of the solution, which is the same computation or similar computation as we did in the previous sections, and we will do some more in the upcoming lectures. Okay, now this is what we had as an example in this section. We will continue with this. All right, now we start another chapter, section, which is about another function, which you will see probably the first time in your life. In 6.5. So this is the impulse functions. or impulse function, or Dirac delta function, or just delta function. And this is kind of a strange thing you will see in a couple of minutes. It's actually not a function. It's somehow a generalized function, you can think. But this is very important to understand the signals and to understand certain problems where you apply a force, but just at one instant, basically you give an impulse to the system. And also we will see one more application of the Laplace transform. Okay, so what do we understand from this thing? So first of all, let me just start with the definition, and then you will see what we are dealing with. All right, so I'm introducing the following function, the tau function. So this is the tau letter. If you don't like this letter, you can use C maybe. This is the notation in the book, so I'm just keeping it. So it's the following function. Okay. So what is this d tau function? So it says that basically it's a locally constant function between minus tau and tau. It's constant, whose value is 1/2 tau. Otherwise, it's completely zero. So if you look at this, this is minus tau, and we have this, this value is 1/2 tau. And it's completely zero otherwise. Okay. This is what we have. Now this, if you think as a force, this force is acting on a time interval between minus tau and tau, and it is completely zero otherwise. This is what we see here. Now, what is the term impulse? Impulse is basically the, as you know from maybe physics, it's the a total force you are applying in a certain period. So if you try to compute it, basically it's just the integral of your force you are applying. So then if I want to compute the impulse of this force, I need to find this area on the given time interval, which is just the integral from minus tau to tau, and of the function 1/2 tau times dt. So I'm not integrating. Actually, you can write the integral from minus infinity to the infinity, but it doesn't mean anything because on this portion and on that portion, it's completely zero. It's all about computation of this part. All right. Then what is this integral? It's constant, 1/2 tau. So what do we get? We have 1/2 tau times t from minus tau to tau. if you plug in tau, you get 1 over 2. If you plug in minus tau, you get minus 1 over 2. So if you subtract them, you basically get 1. So it says that this area is 1. It's obvious, actually. I mean, it's a rectangle. Height is 1 over 2 tau. Base is 2 tau. When you multiply them, you get 1. So it says that the impulse of this force acting on this time interval to a system, you can think like a mechanical vibration problem. So something is moving, and between minus tau and tau interval, you are applying a constant force. Okay? And you want to understand the impulse of this on the system. So it says your impulse is actually 1 unit. So total impulse is 1 unit here. Okay. Now, I want to give the same impulse to the system, but now I want to make my time interval shorter. So then, if I make tau smaller, then the interval I'm applying the force is getting shorter. But this time, I make tau smaller, but 1 over 2 tau gets bigger. So, then if you look at what's happening here, previously, we had something like this. Now, I introduce new tau, I make tau smaller, then we get this one. Let's say these are the new taus. Then this time you will have a bigger force, but acting on a smaller amount of time. Now make it shorter. Then this time this is what we get. So now your impulse is not changing. Your impulse is not changing. It's always 1, but the amount of time you are applying the force to get this impulse is getting smaller. So then what do we get here? If you look at limit as tau goes to 0. Okay? From right, actually. I mean, because tau is the positive thing. So if you look at what is happening to this function, so as tau goes to 0, the intervals are getting smaller and smaller, but your force is getting bigger and bigger. So what's happening then, as tau goes to 0, this interval goes to basically 0. So then what do we get is the following function. Eventually, this function will be 0. When t is not 0, this function is completely 0. So what I'm computing the limit of these functions. For each tau, I have a d tau function. As I make tau smaller and smaller, they approach to a certain specific function. And what is that function? It's the function which is 0 everywhere, except the 0 point. So what is happening 0? If you look at the heights, they are getting bigger and bigger. If you wanted to define, of course, you will say, it must be infinity, but be careful. Infinity is not a number, it's just a symbol. So that's the reason whatever we reach here is just this function. It is 0 everywhere, except at 0. What is special about 0? But if you look at these things, for every tau, the integral of the tau function on the given time interval is always 1. So that means whatever you get here is a function, in quotation marks, which is 0 everywhere except at the impulse point, but its impulse is 1. And so this is a strange function, as you can see. It is everywhere 0 except at 0 here. And but if you integrate this, actually everywhere you get 1. So how do you know? Because this is the limit of these things. So you can see it as the following way. So limit as tau goes to 0. That's what we are doing here. It's constant. So, and if you actually, I'm doing something here. So I'm just switching the limit and the integral, but you can just think that way. So eventually, oops, I made a mistake. This is not this function. This is the d tau function. Okay, so this is the d tau function. So if you look at this integral is always 1. Basically, you are taking the limit of the constant function 1. And so it becomes 1. So as I said, like actually I'm switching. This limit should be here. Then, but using some, again, properties, let's say, theorem, strong things. I'm switching the limit and the integral symbol. So this is what I get. And I know that this is always 1. So the limit of the constant function 1 is 1. So it's strange. I mean, as you can see, like that's the reason you can think like this as generalized function, whatever that term means. But and we get such a thing. So which is 0 everywhere, but its integral is 1. Of course, I mean, and this, by the way, this delta, this is called the delta function. Okay. So it's kind of strange thing. So you can write its shifted version. So let me then write the following way. Delta function or impulse function, delta, or impulse function. Let's say at C is written as the shifted. This is the like impulse at 0. And so this is just defined as 0 when t is not c, but integral from minus infinity till infinity delta function is equal to 1. Okay. 1. All right. Okay. Actually, why don't we find an antiderivative for this function at this point? It's not so crucial, but maybe just an extra information. Remember the Remember the fundamental theorem of calculus. So how are we finding the antiderivative? So basically we're defining an integral. And so let me just remind you. So let's say for continuous functions, of course, I'm talking. So this is not, actually this is completely zero function. But so remember, let's say we have such a function, f of t. So if you look at, let me just do it this way. The definite integral, you can start from anywhere to t, and of f of x dx. If you look at this, FTC says that if it's a continuous function, then its derivative is exactly equal to the inner function. So if you do this thing now for the delta function, so if you try to find like an antiderivative for this, then what do we get? If you think about then, it's all about defining this. It's all about defining, let me just make it 0, okay? Not so crucial. So, or a from a to t. So now, how about in this case, if the small f, like as an example, let's say that our function is the delta function, t minus c, then if you apply this thing from 0 to t, so delta x minus c dx. If you do this, then what do we get? So if you look at now, this function is completely 0. So it's completely 0 if you are not at c. So if I take my t, like between 0 and t now, if you look at this, and if you integrate this portion, you get 0 because there is nothing here. So if you take t here until c, if you look at the integral, then there is no area, so it's completely 0. So when t is less than c, it is 0. But now, when you pass c, then you are integrating from 0 to this t. But now, if you look at this, something is happening at this impulse point. And so, actually, this t doesn't have to be like here. You can just make it further and further. And there is no contribution coming from here. It's all about at c. And if you integrate this at this point, because of the definition of delta function, you get 1. And for the remaining, there is no contribution. They are all 0. So that means that the integral is 1, starting from c. So this is what we get. So as you can see, we are getting the unit step function. So this is what we get. So as you can see, if you look at this unit step function in the calculus sense, this function is not differentiable. It's not differentiable at the c, point c. So actually, if you look at the unit step function, this is c, this is 1. And what's happening is the following. Like if you take the derivative of this function in calculus courses, what do you get? It's completely 0 except at c. Okay? So there is no derivative at c. But if you take the derivative of another constant function, you get the same thing. But I want to understand like this change. So there is a change here, this much. Your function is not the completely constant function. So so it's coming 0, and there's a change happening, and it becomes 1. But in terms of derivative, somehow like we cannot measure it. So the derivative 0, there is 0, nothing is happening, you can think. So but there is some magic happening at C. And so in terms of calculus, you are not measuring because your functions are not enough to understand this change. But something is happening here, like it's moving up. So that's the reason you have to introduce some more concepts here. And basically, delta function is helping us to understand this change. I mean, so it's constant. Again, it's constant, but there's a change happening. And this is measured by a delta function, which is kind of not a function in terms of calculus, but it is basically, I mean, you can think like a generalized function. And we are introducing more concepts, more functions to understand these kind of changes as an extra information for it. Okay. Let me compute the Laplace transform of this and finish today's lecture. All right. But before this, I want to do a quick computation, which will help me to do this. Okay. Let's look at the following thing. So I will just try to compute the integral of, not delta function, because I know this integral, from minus infinity to infinity, times a function. Okay? So I multiply a function with a delta function, and I will try to understand its integral from minus infinity to infinity. So then what is this equal to? Again, the idea is this thing comes from d tau function. So first of all, I can compute the integral of d tau, and then I can take the limit as tau goes to 0. So then I can do the following. From minus infinity to infinity, d tau t minus c, the shifted d tau, and f of t dt. And after this, I can take the limit up. I mean, actually, again, I'm kind of switching these things. Tau goes to 0. This one. But what is this? If you look at this function is everywhere 0 except on a 2 tau length interval around the C, which is basically like an impulse point. So that means that other than that interval, this function is completely 0. So this integral can be written in the following way. So it is C minus tau, C plus tau. So it's like an interval around C whose length is 2 tau. And there, my function is constant, 1 over 2 tau times f of t dt. This is what we have. Okay. So I just need to compute this one. So if you look at this, limit tau goes to 0 from right. This is constant with respect to the integral. So I can take it out, 1 over 2 tau. C minus tau, C plus tau, and f of t dt. This is what we need to compute. Okay, we will come to this. But now, what kind of thing I'm doing here? So I'm assuming here f is a continuous function. Okay? F is a continuous function. I multiply with delta function at C. It doesn't have to be continuous. As long as it's continuous at C, it's fine. Okay. So then what's happening is the following now. So this is C. This is C plus tau. This is C minus tau. And we have a just draw something like this. Let's say that it is like this. Okay. This is f of t. And between c minus tau, c plus tau, and I'm trying to compute the integral of this. Now remember the mean value theorem for integrals from calculus. What does it say? Now, let me remind you what it was saying here, and then I can erase it. So let's say you have a continuous function. You have a continuous function. So between a and b, then you can integrate from a to b and divide by the length of the interval, which is now b minus a. So this is called the mean value of your function. And so this, or average value, f average over the interval ab. Okay? And mean value theorem for integrals says that if your function is continuous, there is a special thing here. There's a special point here, t star, which will take the mean value. Okay? Star will take this value. So there is a point whose value will be the average of your values, basically. That's what it says, right? And so then the integral will be ft star times b minus a. So basically you form a rectangle here by using this average value. Then the integral is the same as the area of this rectangle. All right, now if you apply this thing to our function f, then what does this thing say? If you go back to this, now basically here, if you look at, I'm integrating between c minus tau, c plus tau. The length of the interval is 2 tau, so I 1 over 2 tau. Exactly, I'm computing the average or mean value of this function. So if assume this is a continuous function. If it is just continuous around c, that's enough actually. And so this is going to be the following. Limit as tau goes to 0. And this integral is equal to f of t star. What is t star? T star is such a point here, okay, which takes the average, so whose value is the average value of this, your function on this interval. So that's what it says. So that integral is exactly equal to f of t star. Now what happens now? Of course t star will depend on tau, but we see the following. Now as tau gets smaller, then this t star gets closer to c. Tau gets smaller, t star gets closer to c. And so eventually, if tau goes to 0, this t star will go to c, which says that this limit will be f of c. So integral of a function times the delta function from minus infinity to infinity is nothing but the value of the function at the impulse point c. So strange integral maybe you can think, but its value is very obvious. Just evaluate at the impulse point. So after this computation, now we can check the Laplace. All right. Now, let's try to compute the Laplace transform of delta function at c times f of t. Let's try to compute this. In the special case, when f of t is 1, then we get just the Laplace of this delta function at c. So this is from 0 to infinity e to the minus st times delta function times f of t dt. But now I'm reorganizing it. Delta function times e to the minus st times f of t dt. And I'm extending my integral from minus infinity to infinity because, I mean, it's not important because before 0, this function, I'm assuming, of course, c here positive. So at a positive point, there's an impulse because we are working from 0 to infinity. So that's the reason between minus infinity and 0, this function is completely 0. That's why, I mean, I will not get any contribution if I extend my integral. But then it applies, the formula now here applies. Delta function, something next to this. From minus infinity to infinity. Its integral is exactly the value of this function next to the delta function at the impulse point. So what does this thing say? So this is next to the delta function. So then this integral says evaluate this at c. So we have e to the minus cs f of c. So this is the Laplace. I know, I mean, delta function seems very strange, but it's very useful. It may be frightening, what kind of function is this? But in terms of Laplace, it's one of the easiest functions you will work with. Because its Laplace transform is easy. It's just e to the minus cs. So what happens if c is 0, then Laplace transform of the delta function at 0, delta, t minus 0, you can say. So c is 0. If you plug in c here, then you get e to the 0 is 1. So f here, the function next to delta is constant function 1. Its value at 0 is 1. So you get 1. Right? So Laplace of delta function at c is e to the minus cs. When c is 0, you get 1. So it's the easiest thing you can get out there under Laplace. Because think about, like, you were thinking, constant function 1, but then its Laplace is 1 over s. Sine, cosine, if you look at those things, t square, you always get something in the denominator. 1 over s squared, 2 over s squared, s cubed, vice versa. But this time, Laplace is this delta function is kind of strange, but if you look at its Laplace, there's just numerator, no denominator. Even like when you have something next to that, it doesn't matter, just the value at the impulse point. So in terms of Laplace, it's the easiest function you will work with. All right. So now I'm finishing today's lecture. So I didn't do any example yet for the delta function. Next time I will just start with examples of differential equations where the forcing function is the delta function. And then finally in this chapter we will work with convolution and we will finish it. See you next time.